it's a tiny span of time in astronomical sense. And then stars, of course, after they're born, they have winds that shed out the dust and the gas, and stars shine forth in these beautiful giant clusters. This is the image that came from the 25th anniversary of the Hubble Space Telescope just a couple of years ago. And then we all know that stars, when they live out their lives, they often go through these violent deaths, these explosions that can be either very dramatic, like the Crab Nebula that you saw in the introduction, or can be more gentle, stars blow out their atmospheres, like this example of the Butterfly Nebula. And so we know that our sun will someday undergo a similar process like this, where it will shed its outer layers, it'll grow into a red giant, it'll eventually engulf the Earth. Now this will be several billion years from now, so we don't have to worry about that. But I love the fact that these beautiful images from Hubble really tell us something about our origins. So these stellar explosions, like supernova, are the very events that seeded the universe with the elements that would eventually become planets and eventually become life. So the iron in your blood and the calcium in your bones was literally forged inside of a star that exploded in a supernova. And so what these images really show us is our sort of cosmic connection to the universe. And that's one of the things I love. This is an image of also, still within our own galaxy, of a star that underwent this really complex, confusing event. We still don't really know what's going on with this star, but it's shedding its layers or it's blowing a wind out into the surroundings. So many mysteries out there still. And then beyond our own Milky Way galaxy, we now, of course, know that there are many other galaxies. So this is a nearby galaxy. If you could get outside of our Milky Way and could look back on it, our Milky Way would look probably a lot like this. We think our millions with other galaxies, so they merge with other galaxies. In my own research, I study galaxy evolution broadly. I'm interested in how galaxies change over time, how their stars and their black holes form. And we think this process of galaxy collisions is a really key part of how all of that takes place, of how black holes grow. And we think that there's also gas in the universe that feeds into galaxies that help black holes grow over time. A lot about this process that we don't understand, but we think that galaxy mergers play a key part in the overall evolution of galaxies over time. And then of all the beautiful images that Hubble's given us over the past 27 years now that Hubble's been in space, if I had to pick my absolute favorite one, this would be it. So this is the Hubble Ultra Deep Field. This happened to come out when I was in graduate school, so this is one of the reasons I'm so fond of it. I did a lot of my dissertation research on this image. But this particular version of this image was about 11 days total that Hubble stared into space. And in this image, Hubble's looking at a tiny, tiny little piece of sky. So it's like looking at the universe through a straw. If you held out your pinky finger, you could cover up this teeny tiny little patch of sky. And every point of light you see in this image is an individual galaxy itself filled with hundreds of billions of other stars. And so really what Hubble has given us, in a fundamental sense, is the size of the universe. These deep images with Hubble were revolutionary, and they told us that the universe is filled with hundreds of billions of other galaxies, and all those galaxies with hundreds of billions of stars. Now, in addition to just being a beautiful image, we're able to take spectra of these galaxies, to take the chemical fingerprints of the galaxies, and learn about their distances. And so when we learn about the distances, we can actually make these images sort of 3D. We assign distances to them, and so we can sort of fly through the images in a sense, to get a bit of a sense of scale and a sense of distance for these images. So in the Hubble Ultra Deep Field, again, you notice a lot of interesting things. So you notice as we go deeper into the universe, the galaxies change. They start to look different. Nearby galaxies look sort of similar to our Milky Way, a lot of them. They have spiral arms. They're very large. They have organized structure. But as you get into the deeper universe, the more distant universe, you see a different picture. Galaxies are less well-formed. They're smaller. They're clumpy. They're different. And so learning about how galaxies change over the course of the last 13.8 billion years of cosmic history is still a really important part of astronomy. There's a lot about that process that we're still really need to push further. So as much as we've learned about the universe since we've put Hubble into space, since we started building telescopes on the ground, there's still really a lot that we don't know. And of all of these galaxies, of hundreds of billions of galaxies that we found, filled with hundreds of billions of stars, all of those galaxies, all of those stars, what we know now are probably trillions of planets. Every person, everything that you've ever known, still, all of that, only makes up about 5% of everything in the universe. And the rest of that is what I want to spend the rest of my time tonight talking to you about. So going back to that previous pie chart, so the 5% that we know about, the galaxies, the stars, the planets, that's what we know about. So look now at the 27% that is dark matter. So dark matter, what is it? We have no idea. But this poses a really, really interesting question to us as astronomers. So we don't know what it is, so how do we know that it actually exists? So we have a few clues. The first thing is by looking at spiral galaxies. So you take a spiral galaxy like this, and it looks like it's spinning, right? That's because it is. So back decades ago, astronomers looked at the motions of stars in spiral galaxies. Vera Rubin was actually one of the pioneers of this, an astronomer who did this work back in the 1960s, 1970s. And what you expect to see in spiral galaxies is that as you get out further from the center, you would expect the speeds of these stars and the matter to be slowing down. That's what Kepler's second law tells us should happen. But that's not what we see. So all of these motions depend on mass, depend on the mass that exists from the center out to the stars. And so when we studied the motions in the outer parts of these galaxies, even out further than what we could see, what we found is that there should be more mass there than what we're seeing. There's something there that's causing the stars to move faster in the outskirts. Can't see it at all. And we know it's not gas because we can detect gas in other ways. So not gas, not stars, something hidden in these galaxies that are causing them to move in ways that are unexpected. The second big clue came in galaxy clusters. So galaxy clusters are also a really good way to measure mass. So we can look at individual galaxies and clusters and measure their speeds, fairly easily, in fact. And when we look at galaxies and clusters, we find that they're moving way faster than they should be. So if it was only the galaxies, only the stars, then these clusters should have blown themselves apart, millions of years ago. But galaxy clusters stay together. So there's something there that we're not seeing. And in addition, in these galaxy clusters, we've also, Frank has already pointed out a little bit about gravitational lensing. So what's going on there? So we have this big mass of galaxies and gas, and then beyond that, we have background galaxies, and then over here we have our telescopes. So what's going on with gravitational lensing is that we're essentially seeing the background galaxies being lensed by the mass that's in between them. So this is what theory tells us we should see if there's a lot of matter out there, or dark matter that's hidden that we can't see. And of course, this is what we see when we take these Hubble images. So in these Hubble images of galaxy clusters, you see all these little blue arcs. In addition to the bright yellow galaxies, you see these background galaxies that have been stretched and lensed. So this is a smoking gun for dark matter that exists in these galaxy clusters. This is a very famous galaxy cluster image called the Bullet Cluster. This is actually two galaxy clusters that are crashing together. And so what you see here, again, all this sort of yellow, orange structures here are individual galaxies. The pink and the blue here represents gas in the galaxies that we're able to image in X-rays. And so these two galaxy clusters are crashing together. And we're able to, again, look at sources behind the clusters. And what these images tell us is that all the dark matter is centered on the galaxies and not on the gas. So another third sort of independent clue that dark matter exists in these clusters. So we have all these different independent lines of evidence that dark matter is out there. And so we have a third way that we're able to learn about dark matter by looking basically how galaxies are distributed across the universe. And so just similarly, we're able to map out galaxies at different distances and measure their properties. And those properties tell us, again, that there's mass out there, that these galaxies are moving in ways that indicate that there's matter out there that exists that we can't see. So we don't know what it is. We have a better idea of what it's not. So we know that it's probably not regular stars or gas or planets, because we would be able to see those things. We'd be able to see stars that are bright enough. Dim stars, okay, we might not see the dim stars. Gas we can see from the way the stars are lighting up the gas. But really ordinary matter, baryons, neutrons, protons, and electrons, we would be able to see them in some way, and we can't. So we really don't think it's any of these things. Now, it might be some very, very dim stars, but if those stars exist, they would only be a tiny, tiny fraction of what we think has to be to make up this dark matter population. So we don't think it's regular stuff. We don't really think it's antimatter. So we know antimatter would annihilate with regular matter and produce gamma ray signals that we would be able to detect. We have gamma ray telescopes that would be able to see that. So we don't think it's antimatter. We don't really think it's giant black holes, sort of for the same reasons, because we would be able to see those observationally, see signatures of the black holes in other ways. We don't really see them. So what is it? Well, again, we don't know, but we think what it likely is some sort of yet undiscovered elementary particle that really doesn't interact with radiation in the same way that normal matter is. So that's what we think it is, but again, we don't know. All right, that's dark matter. Not very satisfying, right? We don't know what it is. Okay, dark energy. So almost 70% of the whole universe is made up of dark energy. So what is it? Any guesses? Yeah, we really have no idea what dark energy is. But similarly to dark matter, we know that it exists. And the really strange thing about dark energy is that it's completely confounding our ideas about how gravity works. So it's baseball season. Any baseball fans out there? Orioles fans? Yeah, I would hope so. Okay, so you have a baseball. You throw it up in the air. What do you expect to happen? It comes back down, right? That's our everyday experience of gravity. That's how gravity works. What dark energy tells us is that on large, large distance scales, that instead of pulling, the gravity pushes. So we experience gravity as an attractive force. And what all the physics, all the theory, all the observations are telling us is that at large distances, gravity pushes the universe. And this is completely confounding to everything that we know. Okay, so why do we think this? The first big clue actually won the Nobel Prize back almost 20 years ago now. So this was looking at distant exploding stars, supernovae in distant galaxies. And actually an astronomer right here at the Space Telescope Science Institute, Dr. Adam Rees, was one of the Nobel Prize winners for this really groundbreaking discovery. And so what is it about supernova? So supernova are what we call in astronomy as standard candles. So they have a certain brightness. You can sort of think of it as a light bulb. And so the further the light bulb is away, the luminosity or the brightness of the light bulb goes down. And that's just a very simple physics equation. You know, if you have a standard light, if you measure how bright it is, you can determine how far away it is. And so that's what astronomers were able to do with these supernova. And so we've known for years, since the days of Edwin Hubble back in the 1920s, that the universe is expanding. And so we know the universe is expanding. We know galaxies are moving away from each other. But if all that exists in the universe is gravity, then we would expect that the expansion would maybe be slowing down, maybe be constant. Didn't really know. But when we're observing these supernova, what we found was something really interesting, was that the most distant supernova that we could see were much fainter, or not much fainter, a little bit fainter than what we expected. And so what this told us was that the more distant galaxies that we were looking at with these supernova were moving away from us much faster than we expected. So that means the universe is accelerating in its expansion. Completely unexpected, complete surprise, but the universe is accelerating, something we found out almost 2 decades ago now. And so, again, by studying these supernova was one of the ways that, that we found this out. And supernova have this really great property that they're very constant. So they're normal stars that blow up, and they get really, really bright in a very short period of time, and then their brightness drops off. And so because of the regularity of the supernova, we're able to study them in detail, and again, determine the distances to galaxies, which is what confirmed this idea that the galaxies, the further galaxies, the most distant galaxies that we could observe these in were moving away faster than we expected. So that's the first line of evidence. Second line of evidence is from the cosmic microwave background, which I'm actually going to skip because I'm running a little short on time. We can come back and talk about it if we want. But this third way was again by making these huge maps of the nearby universe and looking at how galaxies are distributed in space. And basically from doing this, we're also able to measure the speeds of distant galaxies. And this was sort of an independent confirmation of how distant galaxies were moving away faster than we thought they should have been. So it's sort of an independent way to measure this dark energy. And there are other lines of evidence that sort of all point to this idea that there's this mysterious force in the universe that's causing it to accelerate in its expansion. Okay, so we have no idea what's causing this. We see that it's happening. We don't know why. We don't know what it is. But we have a few ideas. So what could it be? So it could be some sort of intrinsic property of space-time, something about space itself that's causing the universe to expand. And so Einstein actually predicted this long, long ago. He ended up calling it his biggest blunder because at the time, basically, the leading theory was the universe wasn't accelerating, and now we find out that it is. So it's just some property of space that basically says that empty space is not really empty. It's always sort of creating new space. So that's the cosmological constant, really strange. So the second idea of what it could be is causing this acceleration of the universe is basically a new version of gravity, that we've got our theories of gravity wrong and that we need to modify them. So that would say that general relativity is not quite right on these scales, so maybe Einstein was wrong. And then the third idea, another idea, is that there's really just some kind of new energy field that we haven't really theorized yet, we haven't really figured out yet. So there's these three ideas, and we really don't know. People are sort of leaning towards the first idea, that there's this cosmological constant, but what we really need is more data. And of course, that's where the WFIRST telescope comes in. So the WFIRST stands for Wide Field Infrared Survey Telescope, and it is specifically designed to tackle this question. It's specifically designed to study this effect of dark energy and also of dark matter. So how is it going to do that? Well, one of the ways it's going to do it is to precisely measure galaxy shapes to infer the amount of dark matter that exists in the universe. And this goes back to this idea of gravitational lensing. So any galaxy that's in front of another galaxy is going to distort the shape of the background galaxies, and by precisely measuring those shapes, we'll be able to figure out more about how the intervening dark matter affects those galaxy shapes. And then another way is by very accurately measuring the positions between galaxies. So it turns out that these positions between the galaxies, so if you think of the universe in a three-dimensional sense, the positions that we measure between the galaxies traces directly back to shortly after the Big Bang and to what happened in the universe early on. So that gets back to the very early imprints in the universe for dark energy and dark matter, and all the contents of the universe will help us learn more about that. And then getting back to this idea of supernova, this telescope will allow us to take new surveys of wider swaths of the sky that will help us to determine more supernova, basically to narrow down those measurements and to pinpoint some of these physical quantities of the universe that will help us to establish better distances to these galaxies, just to hone in on these parameters that describe the overall physics of the universe. And so we have these three fundamental things that WFIRST will measure about the universe: the galaxy shapes, the positions, and the distances to these distant galaxies. And so these things will give us hints into different parts of the universe about how structure grows over time, not only the galaxies, but how the galaxies weave together in this overall cosmic web. And then also about how the expansion history works. Again, we know the universe is expanding, we know that it's accelerating, but we don't know what the history of that has been. Has it always been accelerating at the same rate that it is now? So the further out we can push these measurements and the more precise we can make them, the more we can learn about these physical mechanisms that are taking place. And so what this will eventually allow us to do as we hone in on these measurements is really to allow us to determine how the universe will continue, how it will end. If it will end in a big freeze, in a big rip, all of these different scenarios that will allow us to see how we think the universe will continue on. So this telescope is specifically designed to get at these questions of dark energy and dark matter. But the really cool thing about the technology that's going behind building this telescope is it's going to allow us to look back also at the 5% and about one of the really interesting parts of the 5%, which is exoplanets. Now, when I was a kid, we only knew of the planets in our solar system. Now, thanks to NASA's Kepler telescope, we know that planets are literally everywhere. The Milky Way is teeming with planets. Statistically, every star in the night sky has at least one planet around it. That's a paradigm shift. You know, even 15 years ago, we didn't know this. And so what WFIRST is going to allow us to do is a couple of different things for exoplanets. So it's going to help us, first of all, find more nearby exoplanets in a different part of the sort of solar system space or the exoplanet system space. And then it will help us directly characterize some of the closest exoplanets that we know about today. So of all of these different planets, this is, of course, an artist's illustration. Unfortunately, we don't know the details of these planets. Wouldn't it be great if we could actually draw all the planets we know about in a poster like this? But we don't know what they look like. We know there are thousands of confirmed exoplanets. And again, statistics just tells us that there are hundreds of billions of exoplanets in our galaxy, and there's no reason to think they wouldn't be in other galaxies as well. We don't know what they look like, but WFIRST will have the capability to directly image some of the closest and brightest ones. So how do we do that? So all of our best images, actual images of exoplanets to date, are these tiny little blobs. Not very pretty, right? So WFIRST will have an instrument called a coronagraph, which is basically an instrument that blocks out the very, very bright light of a star and allows us to focus in on the planets to better image the planets that are orbiting that star. Now, this is very difficult. Stars are very, very bright. Stars are tiny, stars are bright, planets are tiny, and they're hard to see. And so doing this is extremely difficult, but WFIRST is going to have a new capability to do this in a new way. Now, it's not going to be this detailed. It's not even going to be close, so this is a little misleading. But it's really going to be a new technology, a new way to do this in a really new way. And so just to give you a sense here, this is showing you sort of the area that Kepler looks for and all those exoplanets that Kepler has found. We're launching a telescope called TESS next year in early 2018. It's the Transiting Exoplanet Survey Satellite from NASA. So that particular telescope is going to look particularly at the closest exoplanets in our Milky Way and look close in at the planets that are really close to their star. So what WFIRST is going to do is expand that. It's going to look for the bigger planets that are orbiting further out from the stars. And so it's basically going to help us to, with these 3 telescopes and others, help us to sort of complete the census of exoplanet systems in our nearby Milky Way galaxy. So one of the really neat ways it's going to do this is by a technique called microlensing. So this goes back to the same physics principles as gravitational lensing, is when you have one object that passes in front of another. And in this particular case, you have a star and a planet that's going to pass in front of a background source. And what happens when you have this particular arrangement is that we get a very unique spectral signature that we can easily detect, and that tells us that we have a planet. Now, where's a good place to look for this? In the disk of the Milky Way. If we look right down the throat of the Milky Way galaxy, where stars are packed in, then you're very likely to have this occurrence happening pretty often. And so what we expect with the WFIRST microlensing survey is to see this microlensing effect, these planets and stars passing in front of background stars, to happen very often. And so this is a plot that shows down here on the x-axis, this is distance of the planet from the star. AU is astronomical units. 1 is the Earth's distance from the sun. And here's the planet's mass. So the Earth, right there, 1 and 1. So what Kepler has found, again, has been mostly sort of smallish planets really close to their stars. What WFIRST is going to do is push out to find planets that are more like our gas giants that are orbiting stars, close to our, to our solar system. And so WFIRST has all of these really sort of grand goals. It's really being built to answer some of the most fundamental, puzzling questions that we have in astrophysics today. So how in the world are we going to do this? The key thing about WFIRST is the enormous size of the camera and of the pictures that it will take. So that little square here is the size of the Hubble's camera, so 1 pointing with Hubble. So that Hubble Ultra Deep Field I showed you, all the images of the planets, of the nebulae. So WFIRST will have an area that's 100 times the area of Hubble, and this is critical also with the same depth and clarity that Hubble has. Now we have telescopes on the ground that are able to take these big, wide images.